All right, folks, here we are in the next chapter on comparing two samples. And what we're going to do is look at a couple examples here to get us rolling with this chapter. Each year, so fast food companies, they make a lot of money, and they do a lot to improve customer satisfaction as well as reducing average time. They estimate that for every 6 seconds that's saved, there's a 1% increase in sales. That's like in a $70 billion industry just at the drive-through. That's serious money. That's significant gains in revenue for restaurants. So what we're going to look at is look at some information that came out in 2008 and 2009. In 2009, during 558 random visits to Burger King with a modified order. Modified order just simply means instead of just getting like the number 2, you're going to get like the number 2, no onions. Making sure for the order to be accurate, it must also include like the straw and the napkin, but not like a real complicated order. And they do that consistently. So in 2008, during 529 randomized visits, 477 of them were accurate. So the question is, looking from 2008 to 2008 to 2009, is this sufficient evidence for Burger King that they actually did improve their order accuracy? All right, and companies do lots of things every year to make improvements, so that's what we're going to look at. So what I have is I have two samples here. I have 1 and 2. 1 is my 2008 and 2 is my 2009. And my 2008 numbers were, what did I say? The total N from 2008 was 529, and 477 of them were accurate results. They were accurate. So 477 out of 529, that's like 90% accurate. Not too bad, actually. It seems like mine's always the one that gets messed up. But 2009, then my total number was 558. And my total number of accurate orders was 522. And that was about 93%. Yeah, about 93%. So is there technically an improvement? Yes, 93 to 90. Is that statistically significant? Or that is there significant evidence to show or to prove that they improved on their accuracy with their orders? All right, so that means I'm going to be doing a hypothesis test. All right, and I start with the same thing as I did before. Is this a proportion or is this a mean scenario? I've already kind of indicated it's a proportion because we're measuring how many were accurate versus how many were not. So I want to find out I start with my assumption, and that is from year to year, there is no change. P1 is equal to P2. All right, there's another way that we're going to write this now that we're doing two samples. I'm going to move the P2 over to the other side by subtracting. So it's going to be P1 minus P2 equals 0. Now there is a reason why we're doing this, so just bear with me. My alternative hypothesis is I want to find out, did they improve? That is the proportion in year 2 of accurate orders, is it greater than it was in year 1? Make sure when we're doing this that we keep the 1 and the 2 in the same relative location. So if we're going to say P1 equals P2, then we're going to have P1 less than P2. All right, and then I'm going to rewrite this. So that would be P1 minus P2, so I subtracted P2 from both sides, is less than, and then the right side is 0 because P2 minus P2 is 0. All right, so I'm going to do this, and this is a one-tailed test. Now, I've stated this is what I'm going to do. My plan is the same as it was before. All right, same as it was before. So these are both random samples as stated. Okay. There are over 5,290 drive-through visits in 2008 and over 5,580 in 2009. Ran out of room. 2009. All right. Therefore, independent. There's a secondary aspect to independence, and 1 year's or one sample results or 1 year's results do not influence the other. All right, that is, if I do a sample in 2009, that has no impact on what happened back in 2008. If I do one drive-through visit, that does not affect another drive-through visit because I'm randomly selecting them. All right, so that's my S, and this is my I, and my N is, let's see, there are 529 and, 477 and 522 successes, respectively. There are, oh gosh, I can't subtract well in my head. Looks like 40, 50 something, 50 something. You'll have to actually figure that out. 50 and looks like 46 failures. All are over 10. Therefore, sampling distribution of differences. Now it's called differences because up here I'm taking the difference. All right, so the sampling distribution of differences is approximately normal. Up here, we also would say for independence, therefore, sigma known. We're going to use 2 sample proportion z-test. That's a lot to do for conditions. All right, so keep that in mind for what those conditions are. And now we need to go and do a formula. Okay, so now I'm going to do a z formula. So z equals, now again, remember, it's statistic minus parameter divided by standard deviation of statistic. In this case, though, we're doing a proportion test, and we're doing difference of 2 proportions. So I want to follow the same pattern. So again, when it was a single sample, it was p hat minus p divided by pq over n, square rooted. All right. So we're slightly different than that now because we're going to be p hat 1 minus p hat 2 statistic minus parameter p1 minus p2 divided by, and now I got to do like some side work on this to explain what's going on. In a 2 proportion test, and we're assuming that p1 equals p2. That means I need to make what's called a p combined. A p combined is, again, if I assume that they're equal, that there is no difference, then that means 08 and 09, there's no difference between the 2. So what I have is a total success over total sampled, or total ends. So what I'm going to have is I'm going to have 477 plus 522 over 529 plus 558. So that's handy dandy calculator. 477 plus 522 is 999 And then I have on the denominator 529 plus 558, and that's 1,087. So then 999 divided by 1,087 is 0.919. So I use this in my z-test because I assume that they're equal. All right. And from your formula card, you can look at the, there it is, your formula card. Right here, we have then when there's two samples, and this is for sigma for means, and down here is for proportions. And they list it here, but they don't show it as the combined formula, even though that's what we're doing. All right, so what I'm going to have then is I have square root of, it's a really big square root now. Instead of P1, Q1, I have P combined, Q combined over N1 plus P combined, Q combined over N2. So I'm going to put numbers in here, and that would be, let's see, my P hat 1 is 477 over 529 minus 522 over 558 minus P1 minus P2 from my null hypothesis is 0. And then down here, I'm going to have 919 times 081, if I did my subtraction in my head correctly, plus, oh, this is divided by, that's 0.919 and 0.081 over 529 plus, same numbers on top, 919, 081 over 558. That's a lot of work. All right, but ultimately, what are we going to do? I'm going to come back to my calculator. And now, in this case, we are doing, and I already said on the previous page, we're doing a 2-prop, not porp, prop, z-test. So what I want you to do is I want to go to graphing calculator, get your calculator out, because you're going to have to figure out some of these numbers. I'm not going to give you the final answer. Number 6 is the 2-prop z-test. And what I'm going to do, I'm going to go ahead and clear this out, is on your screen, it says, on the 2-prop z-test, the first thing it asks you for is x1. My x1 was 477. That was the number of successes. All right, my n1 was 529. It asks you for x2, successes from the second year was 522. And my n2 was 558. And I'm testing to find out if year 1 is, remember what my null hypothesis, or my alternative hypothesis, was that proportion 1 related to proportion 2, that proportion 2 was a improvement that is a higher percentage. So that is P1 minus P2 less than 0. And now I'm like trying to remember, is that what I actually wrote? I'll have to go back and look. So anyways, if there's an improvement from year to year, then I'm going to assume that the year 2009 had a higher proportion than 2008. So if I wrote that wrong on my last slide, now I'm like thinking maybe I did. So this is the right way to go. So I want to find out, is this less than 0? All right. So let me go to my graphing calculator and let's find out. 477, 529, 522, 558. And I got my z-score and I got my p-value. what you need to do in the reflection response is write down what the z-score was and what the what the p-value was. I will tell you that the answer is reject the null, accept the alternative. There is sufficient, there is enough data, there is sufficient evidence to show an improvement from 2008 to 2009 in order accuracy. But you need to figure out what the z-score was, and you need to write down what the p-value was using your graphing calculator. Do not do it by hand. So get that done, reflection response, and we'll see you in class.